Okay, our first example is about calculating the prefix sums. Given n numbers, a prefix sum is the sum of the first several numbers. We're supposed to output the sum of the first number, the sum of the first two numbers, and so on and so forth. This example is actually quite similar to the simple summation problem, right? But a little bit more complicated. The technique used here is the same. Use balanced binary trees. So first of all, let's build this tree from bottom up. This is the same tree for the summation problem, alright? And now let's observe which of these numbers are already corresponding to some prefix sums. Obviously, the root corresponds to the last sum, which is just the total sum, right? Next, is this 7 another one? Yeah, why not? That corresponds to the sum of the first 4 numbers, right? And next, is this 2 another one? That's the sum of the first 2 numbers, right? So what is the pattern? Let's denote C of hi to be the prefix sum of the first alpha numbers, where this alpha actually corresponds to what? Where 0 alpha is the rightmost descendant leaf of node hi. What does it mean? For example, for this h and this I, what is the alpha? Alpha is the rightmost descendant leaf. Rightmost descendant leaf. That's 0, 4. And alpha is this 4. So C of 2, 1 should correspond to the prefix sum from 1 to 4. So far, one thing for sure is that when I equals 1, we see that this C is just equal to B, right? So for example, with the root, B of 3, 1 is 16, that equals C of 3, 1, which is the prefix sum from 1 to alpha, where alpha is the rightmost descendant leaf. That gives 8, right? And this B of 2, 1 is just equal to C of 2, 1, because that corresponds to the sum from 1 to 4, and so on and so forth. So one pattern we can find here is that when I equals 1, C of h is just equal to B of h. So this path is done. Okay, now let's check out this one. By definition, what should be the value of C of 2 and 2? By definition, it's supposed to be the prefix sum from 1 to alpha, where alpha is the rightmost descendant leaf, which is 8. So this one is supposed to be the same as the root, right? So this one is supposed to be 16. All right, let's check out another one. Let's check out this node. What is supposed to be C of 1 and 2? It should be the prefix sum up to 4, right? It's supposed to be the same as this C of 2, 1. So C of 1, 2 is supposed to be equal to C of 2, 1, where C of 2, 2 is supposed to be equal to C of 3, 1. Do you see the pattern here? If that's not clear, let's check out this one. This one is supposed to be what? Another 16, right? So what's the pattern here? The pattern is, if this node is a right child, it's supposed to be equal to the value of its parent, right? Because all of them correspond to the same rightmost descendant leaf, right? So here we have another formula. If I is an even number, if it's a right child, then C of hi is the same as C of h plus 1 at the position I over 2. That is the position of its parent. Okay? And how about this left child? By definition, it's supposed to be the prefix sum from 1 to this node, to 6, right? And what we know is that b of 1, 3 is the sum of these two numbers, and this one gives the sum of the first four numbers. So altogether we get 15 for c of 1, 3. In general, it can be calculated according to this formula. If it is an odd number and if it's not along the right path, this can be calculated as what? As the sum of this b plus the value stored in the previous node, which is the same as the previous node's parent. This corresponds to the upper level, and this is the parent of its previous node. Alright? Why use the parent? Why not simply use this value? Because they are supposed to be obtained in parallel. All of them are supposed to be obtained at the same time. So we cannot use the previous value. We have to use the value stored on the upper level. Right? Now, do we have all the cases covered? Yes. So what we do is we calculate b's from bottom up and then calculate c's from top down. And eventually we can obtain all the prefix sums. Let's try to describe it by pseudocode in the WD mode. Step 1, within one part do, we assign all the input numbers to the corresponding b's. Alright? And then from bottom up, we calculate those b numbers. It's the same as the summation problem. And then from top down, so h starts from log n from the root to the bottom 0. And these are the three cases. If I is even, we do this calculation. If I equals 1, we simply copy b, right? If I is odd, then we do the calculation according to this formula. And finally, output all the prefix sums in one part do. Now, what is the total time complexity? These are all part do's, right? So the total time complexity depends on the number of iterations here. It's just log n and log n. So obviously it's big O of log n. And what is the total workload? The analysis is very much similar to the summation problem, right? It's just the workload is doubled comparing to the summation problem, but anyway it's a constant. So the workload is still big O of n. So the workload is the same as the sequential algorithm, and the time is saved. And the trick is that the operations are charged to nodes of the balanced binary tree. And since the task of each node takes only a constant time, the overall workload must be big O of n. And since it is a balanced binary tree, the height, which corresponds to the number of rounds, is big O of log n.